very much. First, I'd like to thank the organizer for giving me a wonderful opportunity to visit Poznan, first of all, and also give me a chance to talk this topic here at this conference. So today I'm going to talk about this title, and broadly speaking, I'm going to talk about multiparameter persistence from the viewpoint of geometric representation theory, known as Kashiwara crystals. So by the way, Professor Kashiwara received the Abel Prize this year, and Kashiwara crystal, who are also called crystal bases, is one of his great achievements, mathematical achievements. So today I'm going to talk about how this concept will be related, actually related to multiparameter persistence. So this is the topic of my talk today. And here's the content. So first, I'd like to study irreducible decompositions of the representation varieties of multiparameter persistence, not indecomposable decompositions. Usually, when we study multiparameter persistence, we first pick some persistence module and try to consider its decomposition using indecomposable decomposition. But this is not the topic of my talk today. I'd like to consider the set of all persistence modules and consider its irreducible decompositions. So this is what I want to study today. And then, in particular, I'd like to show some of the good combinatorial and geometric properties on this representation variety, or also on the irreducible decomposition, which is called Kashiwara crystal. So this is the content of my talk. And here I'd like to emphasize that today's talk is more focused on geometric representation theory than on persistence theory. And actually, based on the results, which I will explain today, I'm now working on connecting these results more closely to persistence theory. For instance, connecting to the interval approximations and so on. And today, due to the time restriction, I'd like to show just a first connection between geometric representation theory and persistence. So this is the content of my talk. All right, so let's begin with one parameter in order to prepare some notations. So as you know, one parameter persistence, which is noted by M here, is given by a series of vector spaces and a linear maps between them. Just a representation on quiver. And then, given such a persistence module, we have a nice property called, provided by Kuller-Schmidt theorem. It says that any persistence module can be uniquely decomposed into the direct sum of the indecomposables. Here J is an indecomposable, Mj is a multiplicity of J, and the I, script I, is a representative of non-isomorphic indecomposables. And in one parameter case, we have a further nice property provided by Gabriel's theorem. It says that indecomposable can be expressed by the so-called interval. Here, interval module from B to D consists of one-dimensional vector space from B to D connected by identity map and zero otherwise. And the persistence diagram is just a collection of those multiplicities at each BD. So this is a standard concept of one-parameter persistence, as you know. And then let's move to multi-parameter setting. As before, we define, so in my talk today, for just the sake of simplicity, I will use two-parameter persistence for multi-parameter persistence. It means that all the results will be valid in an arbitrary dimensional multi-parameter setting. Say, given two-parameter persistence, M, this is again given by representation. On the bound quiver, given by this. Here, GMN, it is also called commutative grid, with size M under N, is a quiver with relation. Here, Q is a quiver, this is a standard notation, I is a set of vertices and E is a set of arrows. S and T are the source map and the target map of the arrows. And here we have C. C means commutative relations. So we assign all the commutative relations in this grid. And the two-parameter persistence is defined by a representation on this bound quiver. Right? And even in this setting, we can apply Plenary theorem, as you know. It means that any persistence module can be uniquely decomposed into the direct sum of the indecomposables. Again, J is an indecomposable, and then script I means a representative of non-isomorphic indecomposables. But here we have a problem, as you know. In two-parameter setting or multi-parameter setting in general, script I will be too big. For instance, it contains non-intervals. For instance, it contains many parameters, continuous parameters, and so on. So in this sense, we can think that indecomposable decomposition based on Plenary theorem is too fine a classification to characterize multi-parameter persistence. And in order to avoid this problem, we have a very nice approach recently developed. It is called interval approximation or generalized persistence, like Tamar introduced as a first day, or also called signed barcode. Those concepts are more or less similar, but sometimes for many cases coincide the same, developed by those authors. And the basic idea of this approach is that given persistence module, given a fixed persistence module, we'd like to decompose that persistence module by using a smaller class of indecomposables. For instance, or especially we focus on only intervals. So in a sense, we try to approximate a given persistence module by using only intervals. So this is the idea how to avoid this problem. But the point here is that still we are using indecomposable decomposition for a given fixed module. And today I will not take this approach. Rather than that, I will consider the set of all persistence modules and try to consider its decomposition property. And, for that purpose, let me first introduce the representation variety. So this concept is very easy actually. So first, given dimension vector nu. So nu is a dimension vector. It means that for each vertex, so commutative grid, for each vertex we assign non-negative integer, and that is used for the dimension of the vector space for the representation or persistence module. Then given dimension vector, representation variety of nu, which is denoted by E of nu. C here means again commutative relation. When I use C as a subscript, it always means commutative relation is assigned. So representation variety E of nu is defined by this. Simply speaking, this is just a set of all persistence modules with given dimension vector nu. It means that this is a collection of linear maps from the source to the target of the oriented arrow, such that it satisfies commutative relations. So this is nothing but a definition of the persistence module. So representation variety again is just a collection of all persistence modules with given dimension vector nu. And here we note that evaluation of our representation along the commutative relation is given by polynomials. So this will be actually an affine algebraic variety in this affine space. So here's an example. So let's see an example. So suppose we have 2 by 2 multiparameter persistence with this dimension vector nu1, nu2, nu3, nu4 here. Then representation variety of this 2 by 2 case is given by 4 matrices A, B, C, D sitting here and here and here and here, such that we have that they satisfy commutative relations. CA equals to DB. In this affine space, here nu1, nu2 corresponds to this linear maps, nu1, nu3 corresponds to this map, and so on. This linear map, the space with the linear map, and so on. And we see that a commutative relation is described by this way in a component wise from ith vertex here to the else vertex to the here. And it is given by quadratic polynomials. So in summary, we have nu1 times nu4 quadratic polynomials that is entries of these conditions. So this is polynomials, set of polynomials. So this will be an affine algebraic variety. So this is an example of the 2x2 case of the representation variety. And moreover, as you can easily notice, this variety has a natural group action induced by the basis change of basis at each vertex. Namely, take a product of the GL with size nu I is the dimension at vertex I. Then this group will act our representation variety as changes of basis, right? And actually, the concept of the representation variety and its group action on it have been studied by several researchers so far in our community. And one of the most famous results is given by Carlson and Domordian in 2009. Actually, they studied the classification and the parameterization problem of the multiparameter persistence by applying geometric invariance theory to the representation variety under the action of group under this group action. So roughly speaking, they consider the orbit space induced from this representation variety, and then consider the geometric quotient, and then discuss this kind of problems. And this is nowadays the most important foundation of the multiparameter persistence. Okay, so this is a representation variety. And then the main player, well, representation variety is also of course important, but also I would like to introduce an irreducible decomposition on the representation variety. So first, let me record the concept of irreducible and its decomposition. And from now on, I explicitly assume that our topology is given by the Zariski topology. And so first, non-empty algebraic set is just a closed set in the Zariski topology. Z is called irreducible if this condition satisfies. Namely, if Z is given by the union of two algebraic sets, Z1 and Z2, then it implies Z itself is equal to Z1 or Z equals to Z2. This is a definition of the irreducibility. And then we have a nice property called irreducible decompositions. Namely, every algebraic set Z can be uniquely expressed as a union of irreducible sets, satisfying this property. So this means that each Zi is maximum, and such maximum irreducible set is called irreducible component. So namely, irreducible decomposition says that every algebraic set Z can be uniquely decomposed into the sum union of the irreducible component. And here's an example. Suppose our Z algebraic set is given by these polynomial equations, xy equals to 0, illustrated like this. Then irreducible decomposition is given by this. One irreducible component is here, x equals to 0, and the other is given by y equals to 0. Similarly, if you have Z given by this, illustrated like this, the one irreducible component is given by Z equals to 0 plane, and the line given by x and y equals to 0. So this is the concept of the irreducible decomposition. And I introduced representation variety in the previous slide. Representation variety of the multiparameter persistence module that was algebraic set. So we can consider its irreducible decomposition. Namely, let me denote by B nu. This is a set of all irreducible components in our representation variety with a dimension vector nu. So this is a set of all irreducible components in our representation variety of the multiparameter persistence. And I take this joint union by changing dimension vectors, which is denoted by BC. This is just a set at this moment. But here, I can briefly explain my main result. Today's my main result is that we can show that a certain combinatorial structure on this set, which is called Kashiwara crystal. So in that sense, this is not just a set. It has a really nice, rich combinatorial structure. And that is a statement of my talk today. So I think now is a good time to explain what it is, what the Kashiwara crystal is. All right. So let me briefly explain the Kashiwara crystal. It is also called crystal basis. Actually, there's a long history of this concept, but let me try to explain some of the important points. So first of all, as before, Q and C means our bound quiver. So commutative grid with size Mn, and the C here means commutative relations. Given bound quiver, let me denote by Q bar the undirected graph of Q, so we forget about orientations. And also let me denote by B, it is just an adjacent matrix of Q bar. And then, given such data, we can define the so-called Cartan matrix, denoted by A, or A of Q. It's easy to define, actually. The diagonal part is just 2, put 2 on diagonal. And on the off-diagonal part, we use the minus of the adjacent matrix. So this is the definition of the Cartan matrix. And here, n is the number of vertices. And then, given Cartan matrix, we can define the so-called root data, which is given by triple. H is a complex vector space. Pi is an n linearly independent elements in the dual space of H. And pi check is the n linearly independent elements in our original space H. We sometimes call alpha I is a simple root, such that ij entry of our Cartan matrix is given by a coupling between Hj and alpha I with a certain dependent conditions. And once we have root data, we can define the so-called weight lattice in our dual space of H. But for just the sake of simplicity, we don't need to consider weight lattice today. Just we consider the lattice spanned by these elements, alpha I to alpha 1 to alpha n. Based on this preparation, we introduce the concept of Kashiwara crystal as before, as follows. First of all, it is given by a data. First of all, we have a set denoted by B. It is also called basis set. And then 5 maps, weight map from B to our lattice, or epsilon I and phi I maps. And also EI tilde and FI tilde maps. Those are called Kashiwara operators from B to itself, or some symbolic zero element, satisfying these conditions. Yes, it looks, at first glance, it looks a bit complicated. But if you are familiar with representation theory of real algebra, or representation theory of quantum groups, those concepts are actually mimicking some of the standard concepts appearing in that representation theory. In particular, Kashiwara operators EI tilde and FI tilde are mimicking the standard action of EI and FI of the real algebra to the representation in such a way that when we apply EI tilde to the basis element, then the weight will be increased by simple root, corresponding simple root.
So yes, what are B and P?
B is at this moment B is just a set. And P and what?
P?
P is a weight lattice.
Okay.
But you don't need to consider weight lattice P. You can just think about P as a lattice defined by this, defined by simple root. And B is constructed for each problem. In our setting, multiparameter persistent setting, B will be constructed by the set of all irreducible components. I'm purposely using the same symbol B, which was used B, C, U or something. Yeah, so B is given by all the set of irreducible components in my talk. But at this moment, this is just an abstract definition. You can think about B as just a set. Yeah, so EI tilde and FI tilde are mimicking some of the standard concepts of the appearing in the real algebra. Yeah, and so this is the definition of the Kashiwara crystal. And I think it is a bit difficult to digest from just definition. And actually, there's a very long history behind this definition. And but due to the time restriction, I don't have enough time to explain those details. So rather than explain those details, let me try to explain some of the important remarks or some of the important histories. How we arrived at, how we achieved, how we reached, how we arrived at this definition, in order to make you more familiar with this concept. So, given quiver, in our case, M by N grid, from that we can define Cartan matrix, and from that, once we have a Cartan matrix, we can easily define the real algebra following the Kac-Moody way, and from that we can define the so-called quantum group. It's similar to the universal enveloping algebra of the real algebra. Quantum group is similar to that, and here small q can be regarded as a variable or parameters. And important point is that the quantum group has a triangular, so-called triangular decompositions. Like given matrix, you have a lower triangular part, diagonal part, and the upper triangular part in the matrix. Similar to that, we have certain decomposition in quantum group. Here, U minus corresponds to lower triangular part, U0 corresponds to diagonal part, and U plus corresponds to upper triangular part. Then, historically speaking, Kashiwara crystal, which was originally called crystal basis, was defined for weight module of the quantum group. So given weight module M of the quantum group, then Kashiwara crystal or crystal basis is given by pairs L and B, such that first of all, this L is a A0 submodule of M given module, which generates M over the rational function field. Here A0 is a subaverage algebra of the rational function field with non-zero denominator at q equals to 0. And next, the basis set B. B is actually Q basis. Q is a rationals. Q basis of this quotient. So in a sense, we are considering the localization with respect to Q. And since L generates M, B can be viewed as a basis of our representation or module at Q equals to 0. And the third condition is that we can, in this setting, weight module setting, we can define the operation EI tilde and FI tilde, which are induced by the standard action of the EI and the FI of the real algebra. And number 3 says that basis element will be mapped to a basis element over 0. Likewise, FI tilde map a basis element to a basis element over 0. Actually, when we apply such operations, usually basis element will be mapped to a linear combination of basis elements from the definition of the basis. But this says that basis element will be mapped to basis element itself over 0. And then number 4 says that EI tilde and FI tilde can be regarded as an inverse operation.
Excuse me, can you say something? Mod use of Q is module. This mod. Yeah.
Here?
Yeah.
It is a module
Q
category.
is a quantum proof.
Say that again?
UQ is a quantum proof,
Yeah.
right? And M belongs, M is an element of mod. What do you mean by the mod?
Module.
MOD. Module. So UQ module.
Yes.
Ah.
And from this definition, actually, once we succeeded in constructing crystal bases, we can show many good properties. For instance, one of the important results is that we can reconstruct character formula of the module by using basis element. Once we succeeded in constructing quantum crystal bases, and actually, Kashiwara explicitly constructed, historically speaking, he first constructed the crystal basis of the irreducible highest weight UQ module, given by this. And based on this success, he tried to generalize. He actually generalized the concept of crystal basis, and that which is the definition I introduced in the previous slide, written in a more abstract setting. And actually, based on that generalization, he proved actually that we can construct the crystal basis of the quantum group UQ minus. So this is a very rough history how Kashiwara crystal was developed. And here I would like to note that everything is written in algebra. Fortunately or unfortunately, everything is written in algebra, and no geometry appears at first glance. But there is a remarkable breakthrough which connects this algebraic concept with a certain geometric property which is coming from representation variety. So where here representation variety will appear. And this is one of the starting point of the geometric representation theory. And in this slide, let me briefly explain some of the histories of the geometric representation theory. As before, given quiver, we can define quantum matrix and its real algebra and its quantum group. And then, first of all, Ringer, famous mathematician, working on the representation theory of the associative algebra, Ringer defined a very interesting algebra denoted by RQ for a given quiver Q, which is called Ringer-Hall algebra. So this is algebra over rationals, and it is an algebra scanned by isomorphic class of representation over Q, over quiver. And the product rule is given by this. Here, representation is considered on a certain finite field. This is important assumption. Representation is considered over a certain finite field denoted by FQ. This Q later will be the same as this Q. But anyway, product rule is given by this. Product coefficient G is given by counting the number of submodule n in M such that isomorphic to M2, and its quotient is isomorphic to M1. And counting the number of such representation. And since we are working on finite field, this will be finite. So this is very defined. So we can just count the number of this module. It looks, well, for me, at first I didn't understand at all what it means. But he proved a really interesting theorem. It says that linear-Hall algebra reconstruct quantum group, in particular, lower triangular part of the quantum group, if our quiver is linking A and then D and then E type. So this is his theorem, still in algebra. But one of the striking results which connects to geometry is given by Lustig. Actually, he generalized Ringer's statement by considering all the proofs geometrically. Actually, the statement is that this isomorphism is valid not only for these quivers, but also for any quivers. And also, we can consider arbitrary field, not only finite field, but also arbitrary field, by considering a representation variety again. Representation variety here is the same as the one I introduced. And that he considered a perverse shifts on it, and then reconstructed this theorem in a geometric way. Not reconstruction, generalized this theorem in a geometric way. So this is one of the starting point of the geometric representation theory. And the message here is that representation variety has a really rich structures. And inspired by this Lustig's result, Kashiwara Saito also constructed crystals geometric way. Here, this is a statement I introduced in the previous slide. Given quiver, we can construct Kashiwara crystal. And they wanted to construct this crystal in a geometric way, in particular using representation variety. The idea is as follows. This construction is really closely related to my main result, so I carefully explain this part. Given quiver, the idea is that they consider the double quiver. Double quiver is easy to construct. For each oriented arrow, we just add an inverse arrow. Just it. Add inverse arrow, which is denoted by Q bar. And then such a double quiver, they constructed again. They also constructed representation variety for each dimension vector nu under some relations, which is called preprojective relation. Not commutative relation, preprojective relation. Preprojective relation is defined in such a way that for each vertex I, we can construct length 2 paths like this, going out and coming back, since we are adding inverse arrow for each oriented arrow. So we can construct length 2 paths, and we sum up all such length 2 paths, and the preprojective relations assign that sum will be there. This is, roughly speaking, this is the definition of the preprojective relation. And then under these relations, they consider representation variety and consider irreducible component of that representation variety that I introduced. In our setting, we consider this kind of the same process in a multiparameter setting. And collected all irreducible components. Then they prove that actually this set, this is not just a set, it has a structure of the Kashiwara crystal. So this is their statement. So this is a rough, brief remarks about the geometric representation theory. Actually, those are one of the starting points of this concept. And the message here, again, is that representation variety has a rich structure. And my work is motivated from this observation. And let's go back to my setting.
Well, let's say, can you repeat this representation variety?
Representation variety is just a set of all representations. The set of all representations. It naturally has a structure of the reductive group. Say again?
Can I imagine something like reductive group?
We don't consider reductiveness.
No.
No. We are considering the quiver representations.
Okay.
And from the background or history so far, there are actually many questions, but I think these two are the most natural questions. First, we need to attack. First question is that, can we construct a crystal for the multiparameter persistence? It means that we define the set of all irreducible components of the multiparameter persistence. So, do irreducible decomposition or does VC has a nice structure or combinatorial structure governed by Kashiwara crystal? So this is the first question. And here we need to note that we need to consider commutative relations rather than preprojective relations. And that this change will actually requires us much effort. We need to do more delicate analysis to show the crystal.
So this representation variety, this is before you do not quotient by these general linear groups. This is before.
No.
This is just sort of, these matrices up to commutative.
Yeah. When I say representation variety, I just mean algebraic variety with action of group, with the action of groups. We don't consider any quotient. But that is a very important comment or question. That strategy will be very important in the proof part. And so this is the first question. Can we construct a crystal on the set of irreducible components of the multiparameter persistence? And the second question is that if number one is correct, can we construct a quantum group for the multiparameter persistence, which gives us actually BC as its crystal? The background of this is that usually quantum group is defined for quivers without relations. But when number one is correct, we have a crystal basis with commutative relations. And historically, crystal basis has a close relationship to quantum group. So it looks natural to generalize the concept of quantum group or construct somehow algebraic counterpart to the quantum group under the conditions that we have relations. And my main result today is answering to number one. Number two is still open. So let me explain my main result. For that, I will introduce a concept. I will introduce a modular variety. So first, those are the same as before. And let nu bar and the nu prime are dimension vectors of our, say, m by n grid. And we consider this set given by triples, phi bar, phi prime, and f satisfying these conditions. Number one, for each vertex, this will be a short exact sequence. Here, dimension vector nu bar is used here, surjective part. Dimension vector nu prime is used for the injective part and the surjective part. And the phi bar is used for injection. Phi prime is used for surjection. So this will be short exact sequence. This is the condition number one. Condition number two, f will be a representation with this dimension vector. So in a sense, f is a representation sitting on this line, central line. F is a multiparameter persistence with this dimension vector. And then number three says that the image of phi bar will be stable with respect to our multiparameter persistence. And actually, from number three, we can construct a sub-representation and a quotient representation from the original representation due to this condition. So this is the meaning why I call this set as a modular variety of all extensions of persistence modules. And then, given this set, so let's take nu bar to be nu minus delta I, and the nu prime be delta I. Here, delta I is a dimension vector where we have one-dimensional vector space at vertex I and zero otherwise, like delta function. Take these two dimension vectors, then we define the following two maps. First, map from here to here is just starting from these triples, going to this representation. It corresponds to sub-representation. So map I1 is defined by just constructing sub-representation from the central representation. This is the meaning of I1. I2 is just taking the central representation. Given triple, we just take this. This is the meaning of the I2. Then I will construct the Kashiwara operator as follows. Roughly speaking, so first of all, we need to define fi tilde and ei tilde, and as I explained, our crystal basis will be given by all the set of irreducible components. It means that fi tilde and ei tilde will act on the reducible component, and the fi tilde will act on the reducible component here in this representation variety, which maps to this irreducible component. One dimension, maybe opposite. Sorry, opposite. Sorry. Fi tilde maps irreducible component here to this. So dimension vector will be arc 1 at vertex I. Conversely, Ei tilde will decrease the dimension vector 1 at vertex I. And likely, this will be defined as follows. For Fi tilde, we first take reducible component here, and then that will be pulled back by pi 1 and pushed forward by pi 2.
Pi 2 is just direct sum of the two representations.
Pi 2? This pi 2?
Yeah.
This is a map from this triple to just picking up this F. So this is this, and this is a representation variety with dimension vector nu. And here nu minus delta I and the delta I are used like this. So central representation has its dimension vector given by sums. So we have when the sum is given by nu. So this will be the set of central representation, and the pi 2 is just picking up the third component. So this is a naive construction. Starting from irreducible component here, that will be pulled back here and pushed forward. But unfortunately, in general, the pullback of the reducible component will not be reducible. It means that we need to restrict to a certain dense open set, which is denoted by lambda bar 1. So lambda bar is an original irreducible component, and the lambda bar 1 is a restriction to a certain open set. Then we can get irreducible set, but still we don't know whether or not this image will be irreducible component or not. It means that that may be smaller irreducible set. So we need to check a certain kind of genericity. So if that is a reducible component, then we will assign that. If not, we will assign 0. So this is the definition of Fi tilde, and the Ei tilde is also defined similarly in the inverse way. And based on that, our main result is given by this. The set of all irreducible components of the multiparameter persistence, and these two operations will actually form a Kashiwara crystal. So this is the main statement. And then, in the
just so I understand. So you're trying to go from, like, let's say, one dimension vector by taking extension to a simple module, right?
Yeah.
Simple and certain extensions produce these operations.
Yeah. Yes. For each vertex I, we put a simple module and then construct an extensions. Yeah.
And do you know, like, for which of these? I mean, I don't know. It depends. Like, how often it happens that you get 0? That this extension is not generic.
How often? Yeah. It's difficult to answer. How often? Sometimes often. I will show. I will show some of the examples later, and you will see some cases which we actually have a 0 as an image. Basically, when we lose genericity, we will get 0. And in the rest of my talk, I will not go into the proof. Rather than that, I will show several examples to understand the meaning of theorems and also to the meaning of the Kashiwara operators. Let's start from the simplest case, one parameter persistence. Even one parameter persistence, we can enjoy this process. Given dimension vector nu, this is the sequence of the non-negative integer from 1 to n. Dimension vector nu. Then the representation variety E of nu, in this case, will be just a vector space because we don't have any relations. In multi-parameter case, we have commutative relations that will assign us non-trivial quadratic relations that will make our representation variety to be non-trivial algebraic variety. But in one parameter case, we don't have any relations. It means that affine space itself with representation variety. It means that it is at the very beginning irreducible. Then in this setting, Kashiwara operator ei tilde and fi tilde for each vertex I can be described by this from the previous main theorem. Depending on each dimension, the large or small relations for the dimensions, we have this kind of operations. And here we see the case of zero dimension. So let's see how ei tilde, the formula of the ei tilde is derived from the main theorem. In our construction, ei tilde construction, we start from the irreducible component here, bigger one, and try to get irreducible component here with dimension 1 lower than the previous one at vertex I. By first pull back and push forward. It means that starting from a generic representation here, central representation, we try to construct a sub-representation. And if that sub-representation is generic, we assign this. If not, we assign 0. So let's see how it works. So here, we have central representation. So F is sitting on here. So given a generic representation in the middle, what we want to do is we study whether or not we can construct the left this commutative diagram. It means that whether or not we can construct sub-representation or this kind of exact sequence and so on. And then from the genericity of F, the rank of this, from the genericity, rank of this should be minimum of nu I minus 1 or nu I. The maximality of the rank is necessary to achieve genericity. And under this condition, we have two cases, this case or this case. For this case, it means that rank of this will be this. This means that this will be surjective. Since this is surjective, we cannot construct this commutative relation. And we cannot construct f prime satisfying this commutative relation. Because we have to be 0 from this path. So since we cannot construct here, we cannot construct sub-representations. It means that action of the Kashiwara operator will be 0. This corresponds to 0 here. On the other hand, opposite case, since we have non-trivial co-kernel of fi minus 1 here, we can use that non-trivial space for the definition of phi prime. And from that, we can construct sub-representation here. That will be, again, generic from the dimension condition. It means that we can construct the map ei tilde to non-trivial. So this is a one-parameter case. Let's move on to the next simplest case, 2x2 multiparameter persistence. Let me denote by this way. Linear map from I to j is fij. So then, in the previous case, the irreducible component was really simple, just one component for each dimension vector. But in this case, when we consider the structure of the Kashiwara crystals, first thing we need to do is to restart all the irreducible components for given dimension vector nu. So let's think about that problem at first. So given our dimension vector nu, so let me introduce this subset in our representation variety, specified by non-negative integer r1 and r2. Given such that the rank of vertically, so we are taking transpose, vertically arranged these two matrices will be less than or equal to R1, and rank of the horizontally arranged these two maps will be less than or equal to R2. So this is just a definition. And then we can show the following proposition. Actually, by using this set, we can restart all the irreducible components of the representation variety of a given dimension vector nu. It says that when our dimension vector satisfies this condition, diagonal part and the off-diagonal part satisfy this inequality, then reducible component is given by actually this set, the collection of this set under these conditions. On the other hand, in the opposite case, like in the one parameter setting, irreducible component is just given by singleton. And based on this characterization of the reducible components, we can explicitly describe the Kashiwara operator. I only described EI tilde case, and the FI tilde case are also similarly described. And let's see how these formula are derived in more concrete example, not abstract setting. So let's think about 1, 1, 1, 2 dimension vector. So this is 2 by 2 multiparameter persistence. Very simple. And in this dimension vector, actually we can check that we have two irreducible components. One is given by this 0, 0 here, and 1, 0, and 0, 1. This is noted by new 0, 2 in the previous notation. Rank of this is 0, rank of this will be 2. And the other one is given by 1, 1 here, rank of this is 1. And 1, 0, and 1, 0, parallel 1. Rank is 1. And actually these two are the irreducible components of this dimension vector. And then let's think about applying E, for example, E for tilde. When we apply E for tilde, then the dimension at vertex 4 will be decreased by 1. It means that when we apply E for tilde, for example, this irreducible component, then this dimension vector will be decreased by 1. And what we need to check is whether or not we can construct sub-representation of this. And in order to have sub-representation, we have to satisfy commutative relation. For instance, in order to have commutative relation between these 3, 4, 8, this vector space will be mapped to 1, 0 due to commutative relation. Similarly, we have commutative relation here, 2, 4 vertices. It means that this vector space will be mapped to 0, 1. This is impossible. It means that we cannot construct sub-representation, so it will be mapped to 0. On the other hand, when we apply Kashiwara operator to this irreducible component, we have dimension vector 1, 1, 1, 1 as before, but we can construct sub-representation in this case. And this is actually generic, satisfying the maximality of the rank conditions. So it means that we have to here. So this is the essence of the Kashiwara operators. All right, so here is the final slide of my talk. Actually, there are, so based on the results today, which found a fast connection, which found a connection between geometric representation theory and multiparameter persistence, there are many questions after that. So first, from the viewpoint of the geometric representation theory, I haven't yet answered to the number 2, question number 2. So number 1 is affirmatively, positively solved. We could construct crystal bases in the setting of the multiparameter persistence using irreducible components. Then the next question is, can we construct a quantum group of multiparameter persistence? As I explained, quantum group is so far mainly defined for quiver without relations. But now we constructed crystal basis or Kashiwara crystal for the multiparameter persistence, which naturally has commutative relations. And historically, quantum group and the crystal basis has a close relationship. It means that maybe natural to have algebraic counterpart of the quantum group even in our setting. This is what I want to consider. And next, from the viewpoint of the persistence. From the viewpoint of persistence, there are many interesting questions, I think. For instance, can we consider geometric meanings of the interval approximations? For instance, what is the meaning of the interval approximation in a setting of the irreducible decompositions? Looks interesting. And also, we can assign invariants. Actually, isomorphism class of representation will be located on a single irreducible component for each. I think English is wrong. Isomorphism class will be located in a certain irreducible component. It means that irreducible component will be an invariant. Then we can study its discriminative power. And also, from the important property of the Kashiwara crystal, we can define the so-called crystal graph. The vertex set of the crystal graph is given by irreducible component, corresponding to invariant. And we have an arrow in crystal graph from vertex I to vertex j if irreducible component indexed by I will be mapped to j by Kashiwara operations. So we have a crystal graph. It means that we can define distance using that graph. It means that we can discuss stability-like stability problems. Yeah, so there are many interesting works, but yeah, so this is the end of my talk. Thank you very much.